Hello, I am Derek MACAKIAGE.
Hi, I'm BAINUO Chen, and we are group 45.
Now I'm trying to explain how the processor works. First, when clock rising once, one current starts instruction sent by PC to ROM, and then ROM reads out 32-bit instruction. First, for ERW instruction, it passes 21 bits to 25-bit base address to read port A1 of register file. The register file reads the register value onto RD1. For the offset of ERW instruction, it is stored in the immediate field of instruction 15.0. Because the 16-bit immediate may be positive or negative, we use sign extend to extend it to 32 bits. The ALU receive SRCA, which comes from the register file, and SRCB, which comes from the sign extended immediate. It is used to add a base address to the offset to find the address to read from memory. And it gives two outputs, 0 and ALU result. When the ALU control signal is sent to 010, it do the addition. ALU result is sent to the RAM. Then the data is read from read data bus and written back to register file, input WD3. And also, instruction 20.16 comes from ROM and sent to address input A3. Register write now gives a control signal 1 to write enable input WE3, which enables the data value to be written into the register file. In addition, the adder here increments the PC by 4 and sends new address to PC again on the rising edge of the clock. That's all the data path for the ERW instruction. Then comes to the SW instruction, which has the almost same data path as ERW instruction, but has an extra data read sent from RD2 to RAM. Because the data memory controlled by memory write now is 1, and the read data is ignored because register write is 0. For R-type instruction, they all read two registers, A1 and A2 from the register file. Now the ALU, as you see here, is 0, so read data from RD2. And the register DST here is now 1, so data 15.11 is chosen and sent back to the register file. And the memory to register now is 0 here, so ALU result is also sent back to register file to WD3. Finally, for BQ instruction, sign immediate pass through a left shift, so it is multiplied by 4, which is added together with the PS plus 4. And branch here now is 1. And using the AND gate here by considering the 0 output from ALU, 1 is sent to the multiplexer. The PC branch is chosen and is sent to the original PC. Now I'm trying to explain the code I write for the square program. At first, I set T1 to 0. And I set T2 to 1. T2 is the order of the number. And I set T3 to 0. T3 is the number of the addition happens. T4 is set to 0. T4 actually has the same meaning of T1. I differ T1 and T4 so that we can display T4 more easily. In the loop, this line is used to add address in so we can display T4 on our FPGA. And give the value of T2 plus T1 to T1, and give the value of T3 plus 1 to T3. And if T2 is equal to T3, we give the value of T1 to T4, and if not, jump to the beginning of the loop. Finally, I set T1 to 0, set T3 to 0, and increment T2, and begin the loop again.
Similar to the diagram shown before, here we have two inputs, A and B, and as connected, like B is connected to the 32 NOT gate, as shown like that. Just 8 NOT gates, just add on to each other into 32-bit multiplexer. We have our functional code input F20. That will come from the ALU opcode that comes off control unit. And then that goes to 32 and through to the 32-bit adder over there. And then that will generate a carry out as well. Then because this is a 0 extend, this takes the bottom, this takes the top bit of the result from the adder and adds 31 zeros on top of it to create a 32-bit number, which will go through to this 4x1 multiplexer, which performs different operations depending on the funct code. So according to here's the truth table. That's the funct code here on the left. This will if the funct code is 000, it will perform A and B, 001 A or B, 010 A plus B, 011 is I don't care. So 100 is A and not B. 101 A or not B, and 110 will set the adder here to subtract, and that will perform a subtraction, and 111 will check if it's less than or not. Right, so probably the most complicated bit of the ALU is how this adder here in the middle is formed. So here in the 32-bit adder, like it's essentially a ripple carry adder of 8 4-bit adders, but these carries are calculated in a different, or using a different technique called the carry look ahead technique, really. So essentially, ordinarily we would have, even here in the 4-bit adder, ordinarily we would input like two 32-bit numbers, A and B, and it would perform every single calculation, determine if it's a carry, if there's a carry, and send that carry on to the next adder in the list, and it'll keep doing that until it produces the result at the end of the 30-second full adder, like the 30-second full adder, like similar to that. However, that will take a lot longer than expected. So the carry look ahead scheme determines a way of calculating the final carry of, like, say, this 4-bit adder. The moment these two inputs are detected or enter the 4-bit adder. So essentially, there's two concepts called this is carry generate and carry propagate. So carry generate is defined as whatever number you put in, if you put in a certain type of two numbers A and B, there'll always be a carry generated. For example, if you put in, like, say 57 plus 65, there'll always be a carry generated of 1. So we call this carry generate. So, but when you're counting in binary, like this is in decimal. When you're counting in binary, like this a carry is always generated when A is 1 and B is 1. So if you have A plus 1, if you have A plus 1 in binary, you'd end up with a 1, 0, and a carry of 1, where that would be the carry. And there's carry propagation, in which a carry is generated if and only if there's a carry input. So like there's the carry put in as an input. So if there's an input carry, like this result will generate a carry. So we use an exclusive OR gate, an XOR gate, to say that if A or B, and only if there's a carry input, will this propagate a carry. So essentially we can define like starting from, assuming we have like an initial carry of C0, we can define the next carry Ci plus 1 to either be a carry generator where G is the predicate A and B. If A and B are positive, then a carry, then this carry will end up to be 1, or if a carry is propagated, if this predicate P propagate is true, and Ci is true as well. So essentially this says if there's a carry in of 1, then this whole block will generate a carry as well. So it's that or that. So in order to actually calculate the series of carries, we use these equations. So essentially C1 would be the initial carry, G0 plus P0 dot the series, where G is essentially just an AND gate of A and B as defined up there, and P0 will be an OR gate or an exclusive OR gate, rather, of A and B over there. So essentially the way we do it would use these equations. So C1 would be C1 would be G0 plus P0 dots and C0, C2 similarly for C3. So this would generate 4 carries like that. Except we'd have to to determine the logic to see what we'd actually implement over here. We rewrite all these equations in terms of C0. So we rewrote all the equations to determine these bits of logic. So C2 would be G1 plus P1, G1 or P1 and G0 brackets of G0 or P0 and C0. Similarly for C3 over there. So essentially this allows us over here so here we're generating P, and here we're generating G. So this could be an exclusive or an OR gate, depending on what you really want to implement, and how many high level schemes you want to do. Since we're going to use this 4-bit carry look ahead to generate a 32-bit adder at the end, we decide to use an OR gate there. So yeah, so essentially this generates a P there, that generates P, and that generates a G there, and we use these bits of logic over here to generate the last carry here, C3, or the carry out, which gets fed into which is the result of each of one of these 4-bit adders, which is just that component that we just closed there, and that generates a carry out, which gets fed into a ripple carry on each of these 4 adders, which creates our 32-bit adder. So this 32-bit adder takes in two 32-bit inputs, A and B, and a carry in as well. So from this carry in, this carry out here is using the logic that I've just explained, is automatically generated as that, well, with a lower delay than it would be if this was a ripple carry adder, and that is ripple carried into all of these adders until we generate a 32-bit sum here at the end.